Thank you guys all for being here today. We really appreciate your time. My name's Anne Marie Weaver, and I've been with LPS now for the last 6 years, and I'm currently the general manager over the manufacturing and the engineering side. Also with me today is LJ Guillotte, our president and COO of Lightning, and he will be a panelist. So any questions that you guys might have at the end, put them into the chat box or into the question box. At the bottom, you'll see Q&A and put them there and we'll address them at the end if we're able to. If we're not able to address it, we'll reach out after and get you an answer to your question. So today we're going to be presenting on successfully pumping the curve with thermoplastic liners. And this was a case study we did with an operator located northwest of Oklahoma City near Deer Creek, Oklahoma. So just a quick overview of what we'll be discussing today. I'll go through a quick background on the history of LPS, as well as a little bit of background on pumping the curve. We'll then get into some specs of our thermoplastic liners and some parameter and force comparisons between thermoplastic liners, bare tubing, as well as rod guides. And then we'll get into the case study. So I'll go into detail on 3 of the wells data, but this case study did have 39 wells on rod pump pumping beneath kickoff point, and 20 wells had line tubing and 19 had guides, and we compare the failure rates at the end. We'll then get into conclusions, and then I'll open it up for questions. So just a brief history on LPS. We were founded in 2011, and our manufacturing facilities didn't become operational until 2016 on the liner side. If you guys aren't familiar with us, we do also manufacture continuous rod, which our manufacturing facility for continuous rod became functional in 2017. And we quickly realized as we began to sell continuous rod, we needed services to be able to install and service the rod string instead of relying on other service providers. And so we purchased Rapid Rod Service in 2017, and we now have service operations in the Permian Basin as well as Bakersfield, California. In 2020, we purchased our first EMI unit because, as we realized over time, one of the historical downfalls to continuous rod has been repeated rod failures. And so we purchased our first EMI unit to be able to scan continuous rod at the well site. That EMI unit has evolved a lot over the last 3 years. It's basically now the size of a shoebox, and it's a really pretty quick, handy setup to where we're at today. So in 2023, we launched our high-rise system, which basically encompasses everything I just mentioned: our continuous rod product line, our line tubing product line, our EMI services, and our rig services. All right, so jumping into the presentation. So we know that the traditional approach is positioning your pump in the vertical section, and you have that advantage of not pumping through that significant deviation. Although with these horizontal wells and the shallow kickoff points, you are still usually pumping through some pretty significant deviation up top. But when it's no longer economical to lift these wells from above kickoff point, you may want to lower your rod pump into the curve or to the lateral portion of the well to reduce the producing bottom hole pressure on the reservoir and therefore increase that drawdown. So by increasing your drawdown, you're able to increase your production, but a lot of the times you'll see those increased failure rates due to pumping through that significant deviation. So there's several solutions that operators may try and implement to help reduce these increased failure rates. So operators look to install guides beneath kickoff point, specialty types of tubing, continuous rod is an option as well. And then obviously thermoplastic liners, which we're going to be discussing today. So today we'll be focusing on thermoplastic liner, which was what this operator used. But again, we're going to be comparing it to rod guides because they also had 19 wells on rod guides as well. So if you've never run line tubing in any of your wellbores and you're not familiar with it, it's essentially a thermoplastic liner that we extrude into the shape of a pipe profile, and we mechanically bond it to the tubing string. So what this means is when we get like a load of tubing in at our manufacturing facility, we'll actually measure the ID of the tubing string, and we'll extrude the liner to a bigger OD than the ID of the tubing. And then we'll mechanically roll that liner down and stuff it into the pipe. So you have an extremely tight fit. So that's what we mean when we do say that we're vertically integrated. It's one of the advantages that we do have. We offer various resins to match your downhole wellbore conditions, so I'll discuss that in detail in the next slide. And another advantage of line tubing is we can bond it to new tubing, but we can also bond it to used yellow or blue band tubing, which is really beneficial to a lot of our operators the last couple of years when steel prices for tubing were extremely high. So some of the benefits of line tubing: it prevents that rod on tubing contact, eliminating steel on steel wear. And so you'll have increased run times on your tubing string as well as your rod string. It prevents your tubing from corrosive reservoir fluids, eliminates the need for rod guides. So you do not want to run guides through the line tubing section. And it does have a lower coefficient of friction than bare steel or steel on steel, and as well as guides. And so that reduces your loading at surface as well as on the rod string. And I'll discuss that in more detail in a couple of slides. So these are the liners that we offer here at LPS. So determining the best liner for your well's condition is really important. You don't want to run, past the max temperature that it says here. So LF115 that you see highlighted in LF115, this is our flagship resin. It's the affordable crystalline resin that we offer. And LF60 and LF99 are amorphous resins, whereas LF115, LF115B, and LF170 are crystalline resins, and they are a bit more dense than these amorphous resins, and so they're able to handle wear better. And so in the case of pumping the curve, I lean towards recommending a crystalline resin due to the severity of the deviation and the often high resulting side loads, because they're going to wear at a slower rate than the amorphous resins. One thing I just wanted to point out, LF115B is our cold weather LF115. So we're now in the Bakken, and basically the processes of how it's bonded to the tubing is a little bit different than the LF115. So if you have any questions on that, we can get into that further post-webinar. So on this slide, we just wanted to show you, the difference in the drag force between 3 different cases here. So we really want to show you the benefits of having that lower coefficient of friction on this slide and the next slide. So we have 3 cases. We have conventional rods on bare tubing, conventional rods with guides, and conventional with thermoplastic liners. And the data that to calculate the drag force, you need the normal force and the coefficient of friction. And the normal force is used, you calculate it based on this equation up here. And so what we did is we took a well from the case study, well number 1, which you'll see more data from it in a few slides. And we just chose a point beneath kickoff point to calculate the normal force. So you need the length of the rod. So in this particular calculation, we're just looking at 1 25-foot stick rod section. And you need the weight of the rod. So in all 39 of the wells, they ran 7/8 stick rod, conventional stick rod, beneath kickoff point through the curve. Again, 19 with guides and 20 with liner. And then they have the fluid specific gravity. We ran 1, and then an inclination angle of 48 degrees. And there's about 500 feet to the pump beneath that. So the seat nipple depth was around 7,000 feet. And so to get the normal force, we inputted that, and you can see the result right here. So around 36 pounds. And all you do to get the drag force is just multiply by the coefficient of friction. So for steel on steel, multiplied by 0.2. For rod guides, multiplied by 0.25. So this is the value the operator was using for their guides. This can range, it can be lower or slightly higher, just depending on the material of your rod guide. And then 0.1 for thermoplastic liners, which has been what we've used, and we've been able to verify this value by comparing predicted loads from RodStar SRod to actual loads in the field with some of our customers. And you'll see one of the cards in this presentation. So you can see the resulting drag force here when you're comparing thermoplastic liners to steel on steel, it's about half. And then when you compare it to rod guides, it's about 2/3 of that. Just to point out before I move on the next slide, this drag force is only for this particular point. To get the correct drag force at 6,600 feet, you'd have to sum all the drag forces beneath that, which is going to change at every measured depth due to the changing inclination angles that are occurring. Okay, so moving forward, so we just ran a few cases in RodStar SRod to compare to kind of just see the benefits again of the lower coefficient of friction. So we ran steel on steel, steel with rod guides, and then steel with thermoplastic liners. And this is using that same well that I showed you on the previous slide. And one thing I did want to mention is we ran the entire wellbore with guides and with liner. In reality, you'd only do it where it's absolutely necessary. And you'll see in the case, they only ran liner and guides beneath kickoff point. But you can see that obviously the lower coefficient of friction, the more liner you run, the more benefits you have. So you have a much lower gearbox loading when comparing to steel on steel, as well as rod guides, as well as a much lower peak polish rod load, electricity costs. Your rod loading decreases, so you'll have increased fatigue life on your rod string. Your side load is substantially reduced because it's calculated based on your peak polish rod load. So with that, having a much lower peak polish rod load, your side load is less. And then your downhole stroke is considerably increased due to the less friction. And so you're able to produce more. So, okay, now jumping into the case study, I wanted to give you a little background on the area that the subject wells are located in. It's in the West Edmond-Hunton Lime Unit, just northwest of Oklahoma City, and was originally drilled in the 1940s. The operator that we worked with took over operations in 2018. And the previous operator that they took it over from began drilling horizontals in 2005, and they have over 80 horizontal wells drilled to date. The field is known to have a very low bottom hole pressure due to the continued drawdown over the last 8 decades. And so the initial bottom hole pressure is below 500 PSI, making it almost impossible to artificially lift these wells above kickoff point. So new wells are artificially lifted with an ESP below the curve at between usually 75 to 90 degrees for all other wells inclination, and then converted to rod pump as the fluid rates do decline. So as mentioned on the last slide, due to the low bottom hole pressure, 200-foot tangents were drilled anywhere from 75 to 90 degree inclination in order for them to successfully run their ESPs. As production drops below 200 barrels of fluid per day, or if they were experiencing numerous ESP failures, that's when they would convert their wells from ESP over to rod pump. And as you can imagine, the friction from the rods through the curve made it really difficult for them to pump efficiently. So after modeling different rod designs and many field trials between guides and thermoplastic liners, they determined that installing thermoplastic liners beneath kickoff point and through the curve was the most efficient method for them to pump the curve. Okay, so jumping into some of the well data, they had 3 different wells that I'm going to show you to be converted from ESP to rod pump, where they modeled rod designs using RodStar as the predictive model with both thermoplastic liners and rod guides through the curve. We then did follow up on this particular well. They had an actual downhole card to determine how close the predictive model was to their actual loads in the field. So shown in the table here, you can see quite a bit difference comparing the 2 cases. You can see one thing we really want to point out is we're modeling an 18.5-inch difference in downhole stroke length, a 16% decrease in gearbox loading, a 5% decrease in peak polish rod load, and a 12% increase in minimum polish rod load. So you have a better minimum polish rod load to peak polish rod ratio, which has been proven to help increase your run times. And one issue that we caught when running through the different models, RodStar estimated almost the exact same production, even though there was we were running the same pump and the same strokes per minute, which but you had a considerably longer downhole stroke. So we went ahead and calculated it ourselves using this equation from the sucker rod pumping manual textbook. And we got a pretty substantial difference in production when comparing liner to rod guides. So around 290 barrels of fluid per day and 330. And then showing you the deviation survey here, the light blue is bare tubing, and then the blue is where the wells kicked off. And then this is also where they ran the line tubing. So you can see the pump, the seat nipple depth was around 7,100 feet. And this well actually did have a pretty high dog leg in the first 1,000 feet. And I believe they ran guides here. So here's the actual pump guard after converting the well over to pumping to rod pump with thermoplastic liners. So the actual results are almost spot on to what the operator was modeling in terms of peak polish rod load. And one other thing that I wanted to mention, they didn't have a well that had both thermoplastic liners and rod guides through the curve. So like they didn't have a well that had guides, pulled it out, and then they installed line tubing on. It would be something that they're planning to do in the future, but they don't have any comparison that has had both in the exact same well. So here's the production for this well before and after from ESP to rod pump. So you can see the failures shown on the graph. The production, so green is oil, blue is water, and red is gas. And a difficult question for the production engineer that was over this field that he had is when to convert these wells over to rod pump, which I'm sure, many engineers face the same question when they're changing lift types in their areas. So as mentioned, for this particular operator, a good rule of thumb for them out in this field was to convert around 200 barrels of fluid per day to rod pump, but sometimes it was necessary for them to convert earlier if they were experiencing numerous ESP failures, as they did for this well. So converting this well over to rod pump with thermoplastic liners drastically reduced their failure rate when comparing it. Obviously they were having multiple ESP failures, and they did lose a little bit of production, but they were able to increase their runtime and by almost double by not having to constantly work the well over. So this graph here, this shows the electrical savings from converting over to rod pump, from ESP to rod pump, to help show that not only did they save on workover expenses, but they also reduced their LOE. So again, they did have some production loss, but the graph on the right shows their lifting costs broken down by dollars per BOE to show the overall power efficiency comparing the two. So it's almost $2 per BOE that they saved from converting to ESP to rod lift. Again, it would be good if they had the same power usage for rod guides through the curve in the same well to see what it does to cost having to pull a higher load, since it would be a substantially higher load with that significant of deviation. And it's something that they hope to plan to do in the future. So moving on to well number 2, again, here's the data comparing the two different models, liner to rod guides. There's a 10-inch difference in downhole stroke length, 7% difference in gearbox loading, and then a 4% difference in peak polish rod load, and the minimum polish rod load increased by 16%. So again, you have that higher minimum polish rod load to peak polish rod load ratio. You'll notice on this directional survey that the kickoff point was around 5,000 feet, which for this particular field, it's usually around 6,300 feet. And this well was drilled by the previous operator, so they weren't sure why the well was kicked off so high, but with the higher kickoff point, it only made it more difficult to pump above the curve. So as similar to well number 1, they were experiencing multiple ESP failures, as you can see, before they converted to rod pump. And after conversion, they were actually able to maintain fluid production, as you see, and they actually increased gas production. If you can see right here, this is when they converted. And this was due to not having to fight the ESP gas locking constantly. And they also, like the previous well, saw an improvement in their failure rate reduction on this particular well, due to the numerous ESP failures. So moving on to well number 3, predictive model. So this one was converted at a little bit less fluid. You can see, 130 barrels of fluid per day. Predictive model shows a 3.6-inch difference in downhole stroke length, 4% difference in gearbox loading, and a 4% difference in peak polish rod load, and 11% increase in your minimum polish rod load. So again, you have that higher minimum polish rod load to peak polish rod load ratio. Lastly, so you can see the deviation survey here. So more similar to the first well that I showed you, you have, bare tubing up here. You have kind of a high kickoff or high dog leg in the first 1,000 feet, like the first well. And then they ran the thermoplastic liners beneath kickoff point through the curve until where they set the pump. So on this well, they didn't experience as many ESP failures as the first two wells that I showed you before conversion. But since the fluid production was, lower than their 200 barrels of fluid per day, they went ahead and converted the well over to hopefully get ahead of those potential failures. And after they converted, production was maintained back on the decline curve after conversion to rod pump. So this is their overall cost comparison. So with the 80 horizontal wells in the field, they have about 40 wells or 39 wells that are actively producing on rod pump and pumping through the curve. So the original design was to use rod guides, but as they started to model and run field trials, they determined that running thermoplastic liners was the route to go. So in the past 4 years, they saw a failure rate of 0.68 failures per year with thermoplastic liners compared to a little over 1 with rod guides. And so you can see the investment per well here after kickoff point, like for the liner and the guide. So this is just ran beneath kickoff point. And one thing that I wanted to mention is, so they had 7-inch casing. So they were running 3.5-inch line tubing, typically with an 1.5 to 1.75 pump, just depending on how much fluid they were making. But they were actually able, in a couple wells, they were actually able to directly offset this liner cost because due to significant deviation, they were running mainly, all steel strings, but they were able to use a 640 unit instead of a 912. The engineer said on a couple wells due to the lower coefficient of friction with the line tubing. And so they were able to directly offset this liner cost by purchasing a smaller pumping unit. And then if you'll look to how much they were spending on the repair costs for a hole in tubing and a rod part or a pump failure, you can see here that it's a smaller operator, so their costs are probably lower than what most of you are typically deal with. But we just multiplied this by the failure saved versus guides versus liner. And so depending on if it was a rod pump failure or tubing failure, you're saving roughly on average $4,700 per year per well. And you multiply that over the 20 wells, this equals a savings of $94,000. And a couple other things that I wanted to mention that happened on some of their other wells. On one well, production was less after conversion. And so after a couple of weeks of runtime, they actually pulled the tubing and ended up installing a velocity string and a gas separator to help push the gas up the annulus versus attempting to pump it up the hole. And after doing that, they were able to actually get their production back to previous decline. And then lastly, one of the wells in the study also had continuous sand production, and due to the inclination, it hindered some of the solid separation. So that I just wanted to point out that obviously installing liners that isn't a solution for that. Most of their wells, they didn't have any solid issues, so a standard mud anchor did work great for them. So just wrapping up the presentation today. So they were able to maximize their drawdown and therefore increase production on their wells, while also decreasing their failure rates by installing thermoplastic liners versus rod guides. And by using thermoplastic liners, they were able to reduce some of their system loading and actually purchase smaller pumping units, as well as increase the life of the equipment. And with that, again, we just want to thank you for your time. Appreciate it. And we know you're all busy, and we'll go ahead and open it up for questions. So I will pull up the question box. Okay, so I'll go ahead. I'll either address it or I'll ask LJ to address it. But we have a question on, is there any inclination or DLS limitation, any rod failure versus inclination DLS analysis? So don't have specific analysis, but I do know that most of the wells, their pumps were set beneath 5 degrees dogleg severity. And they had a few that they had to set above 5, but they always tried to stay below 10. And on the ones above 5, they did see higher failure rates with their pumps. But that 0.68 failure rate that you see for thermoplastic liners, this has been asked before. is actually mainly pump failures. They didn't really see any tubing failures or rod part failures. The next question I have here, I'll take this one as well. What was the hole angle where pumps were set? So they had about all the wells, and I can get into more detail and actually send you the data they had specifically for each well, but usually they're between 75 to 90-degree inclination, and again, ideally below 5-degree dogleg severity. Okay, LJ, I have a question for you. Can you run rod guides through the line tubing?
Yes, thank you, Ann. It's not necessary to run rod guides, and it's not a recommended practice, as rod guides create additional friction with the like material rod guides and liner. And also it increases the amount of friction. So it's not a recommended policy practice, I should say, Ann.
Perfect, thank you. And then I have another question for you, LJ. How do you inspect line tubing before rerunning?
The inspection of line tubing before running and when pulling the wells after it's been run is mostly conducted via a visual inspection, shining a flashlight through the inner diameter of the pipe, 32.5 foot. We can see any ripples or cuts or gouges in it from the naked eye. Additionally, we can take it a next step and run a bore scope through it. It's a camera in essence that would do a further, more detailed inspection, but a visual inspection typically covers it.
Perfect, thank you. And then I have another one for you. What's the thickness of the liner of the 2 7/8 line tubing?
2.0.
Yes, I can elaborate. So yeah, 2.0 drift, and then so it's about 0.14 wall thickness. So basically, just to elaborate, any of our liners basically almost drift down a tubing size. So 3.5-inch line tubing drifts around 2.5 inches. So about almost the idea of a 2 7/8 bare tubing. And then, okay, so we have a few questions here. Did they clean out the heel or the lateral before conversion? I do not know the answer to this question, but I can reach out to the engineer and I will we'll get back to you. Were they running sinker bars in the curve or keeping them in the vertical? So I should have mentioned this during, but I guess I forgot to. So they actually, most of their rod designs were 1-inch 7/8 stick rod, and then they run about 700 or 800 feet of sinker bars beneath kickoff point. And then they'd, in all 39 of those wells, they ran 7/8 stick rod through the curve. So usually it was around 1,100-1,200 feet of 7/8 stick rod beneath kickoff point. Were they setting the TAC at the kickoff point? If so, slimline or Baker style? I also do not know I'm sorry, but I do not know the answer to this question as well, but I will reach out to the engineer that we worked with, and I will send you the answer. And then were rod rotators or tubing rotators used? They were using rod rotators. I'm not sure specifically which one, but they were using rod rotators on these wells. So we have a couple other questions. LJ, I have another question for you. How is the liner affected by H2S and CO2?
Well, that's a good question, and it really depends on the type of composition of the resins that are used to extrude these thermoplastic liners. They're all high-performance resins. Each, depending on the composition of the resins that are being presented, each one has a different permeation coefficient, if you will. So taking in, for instance, the LF115 product is in the crystalline family of polymers, and it has a polyolefin ketone. So in this particular one that's been tested in labs, as well as our experiences on CO2, is almost to 100% CO2 exposure with the LF-115 liners. H2S is typically running at about 2% exposure, 2 to 5%. 5% would be the extreme high side. So it all depends, but those are the guidelines.
Perfect. Thank you. Another question I'm not sure I'll be able to answer, but I again can reach out to the engineer. Were the conventional rods with T-class couplings, excuse me, any precautions on those? Would you have study results on comparing T-class for spray metal? So we don't directly have case study results comparing T-class versus spray metal, but we do know that we recommend spray metal versus T-couplings because sometimes those T-couplings are more susceptible to corrosion, and that corrosion sometimes can peel the liner depending on how corroded those couplings get. I'm not sure in this particular case study if they were running with T-class or if they were running with spray metal, but I can definitely find out for you. LJ, this is a good question for you. Do you know of any operators utilizing line tubing for disposal wells?
Yes, it is used in disposal wells, although the most common method of it is a baked on, sprayed on epoxy base like a TK99 or TK80 from NOV. However, as the resins in the LF-115 being an excellent product with low permeation, it's used in CO2, used in injection wells as well, disposal wells and injection wells. I don't know how many operators are practicing that. I do know that there has been operators that use thermoplastic liners versus a sprayed on epoxy coating.
Perfect. Thank you. I'm also going to address this one to you as well. We have a great question. Have you had any installs in the Bakken? How do they compare to the study in Oklahoma wells? We know that I'll let you take this, but it's deep. They said the wells are deep, highly deviated in the Bakken, coupled with corrosive gas, presents large challenges to pumping these wells beneath kickoff point.
Very good question, and to the audience. Thermoplastic liners by nature have pros and cons to any type of application you apply in cold weather, hot downhole temperatures, especially with extreme temperature swings. Historically in the Bakken, thermoplastic liners have not had a good reputation, good performance, if you will, due to the popping of the pin ends, which is on the chamfer side that Ann showed you earlier in the presentation, where it's a hot formed pin end. So when you have a temperature swing from 30 degrees or more within an hour to dropping from, let's say, 55 degrees to the below zero, like any thermoplastic liner, it acts like a sponge. So it has some permeability to it. So if it shrinks, the pin ends were popping off. There's been some experiences in new testing, as we are as well, running our LF-115B liners that Ann spoke to you about earlier. We've changed the process of that. We also added a blend to our LF-115 resins that gives it a little bit better coefficient of expansion, if you will, that's preventing those pin ends from being compromised at surface. Most of your failures will occur at surface, not once you get it in the hole or when you're pulling the liners, pulling the tubing out of the wellbore. But based on the process changes that we've been implementing and the change in the blend of the resins that we're using on there, we're seeing good results through this year for sure. But there's been good results that have been proven over the last 2 years with operators who have been using these liners in downhole applications. So we're excited about the new product line rolling up there. We have about 18 months of experience in that market. As we know today, coming out of it, our liners are performing well at surface as well as downhole. And an acceptable failure rate at surface is usually something between 2% and 5% of failures at the surface of a total. So if you have a 220 joints, 2 to 5% poppage before you run it in whole is an acceptable. I mean, you're going to have some of that. So don't want to paint a picture that it's 100% of all the joints will survive severe temperature swings. But on average, a 2% is a really good success ratio. Makes it a viable solution for the Bakken operators. Back to you, Ann.
Thanks, LJ. Got another good question. Do you have any experience with continuous rod and thermoplastic liners together? So we do. I would say is an ideal solution for pumping beneath kickoff point. We also have several wells with a customer in the Permian with just continuous rod beneath kickoff point. And then we have many wells with continuous rod and line tubing. So both are great options. This particular operator, since they were in Oklahoma, there's no services for continuous rod there. So that's why they focused on line tubing, but obviously they saw good success with the liners beneath kickoff point. And I can send you some more data in detail, but we have had good experience with continuous rod and line tubing, both beneath kickoff point. LJ, I have another question for you. What protects the coupling from corrosion when using line tubing?
Yes, we apply a sprayed on, baked on epoxy, Xylene 1500. And the reason that works in the coupling versus that on the tubing, if you're familiar with sprayed on epoxies such as Tuboscope over time, those have a tendency for cracking and chipping due to the deviations in the wellbore and the production tubing of a 32.5 range pipe bending through there. You'll see cracking and chipping. With a coupling, it's rigid. It does not flex at all. So that's the product that we use on it, and we're successful with that from corrosion.
Thank you. We got another question. Can you line customer-owned, used, inspected blue or yellow band tubing? LJ, you don't want to take that, or I can address it either or.
Yeah, no problem. We do line used tubing successfully. However, the most common practice is with white and yellow band. With blue band, it's a little bit more difficult, but we can line it for sure. The bonding mechanism, the bonding of the lining and the tubing. So if you can imagine, as you have pipe corrosion in the ID of the pipe, the actual surface that's bonding with the liner being a smooth surface, and a rough surface of used tubing is worse as you go from yellow, blue, green band. So that bonding effect becomes less effective in the more corroded or yellow, blue, green band. So most of our customers, we had a lot of that through 2021 and 2022, especially when we saw the price of steel skyrocket, as well as availability. We had a number of customers and a demand rising for used tubing, lining that used tubing. Yellow band, we have an extremely good success ratio with that. Blue band, I would say you're gonna start compromising the run times of what the projected run times would be with new steel in liner. So you'd have two smooth surfaces, which have for all intent purposes 100% contact between the two. With the yellow band, you lose a percentage of that, 15%. Blue band, you lose another 15% of that to 45. Likewise, so when you compromise that bond, it also compromises the functionality of that liner and the predicted run lives of any liner. But absolutely, it's a common practice for us, yellow and blue band most commonly.
Thank you, LJ. We have another good question here. I have quite a few wells in the curve that see a lot of pump failures due to wear at the top of the pump. Are you guys not seeing these types of failures, as well as rod parts? So for this particular operator, and just in general as well, line tubing is not going to help with your pump wear. The key to prevent pump wear for this particular operator was to try and land your your pump at the lowest dogleg severity as possible in the curve or in the tangent. But of course, your pump, is still going to wear quicker since you're, pumping on its side rather than in the vertical section. However, the liner does allow them, to run almost all the way to 90 degrees with that reduced friction throughout the system. And their lowest DLS, usually, I would say on average, their pumps were set, 85, 86 degrees inclination. And they also rarely saw rod parts as well with the line tubing. So again, that failure rate of 0.68 was primarily comprised of pump failures. And then we have another question. The type of mud anchors run, did they have any issues as you don't have gravity working for you? At least not as much. So I kind of touched on this at the last slide, but they had one issue with one of the wells with liner that had continuous sand production. And so they were unable to run any sort of desander at that inclination. So that obviously hindered them on solid separation. And so most of their wells actually didn't have any solid issues. So a standard mud anchor for them worked great. And then I have one other question, another great question here. Are you using any type of special pumps? Have you ever had any issues with pumps being set horizontal? No, so they didn't have any issues with they weren't using any special pumps. They were just running normal RHBC pumps, and they didn't have any issue pumping fluid at the inclinations that they were setting at. So I think if it's obviously set past 90 degrees, you would see some issues of being not being able to pump, but they were set around 85, 86 degree inclination and never really had any issues. And then one last question here. We're going to end here at 10:45. So did you run gas separators on all 5 wells, or all 3 wells, excuse me? And if so, what type of gas separators did you run, and how did they work operationally by being below kickoff point? So the wells with higher GORs, they would run the velocity strings that I mentioned on one of the last slides. And they worked great for them with no issues. Obviously you need to be careful. And then they were in with a Packer style gas separator. So obviously you need to be careful setting and releasing your Packer at that inclination. But they didn't have any issues to date. And they have, I think, over between 10 and 20 Packer style gas separators set in the ground with multiple pulls over the past several years, and didn't have any issues at that inclination. So it's 10:45. Again, we appreciate your time. If we didn't get to your question, or if I wasn't able to answer it, I will reach out to you after talking with the production engineer and shoot you an email with an answer to your question. Appreciate the time as well as the questions. Thank you guys, and thank you, LJ.
Yeah, thank you. We appreciate your time.